We can get started. Just another reminder for the new joiners, we are recording today, but you still should feel free to ask questions. I can help edit if you don't want to end up in the recording. You can also post in the chat, which I can help relay. So do all the usual things that DLCT allows and encourages. All right, floor is yours, Elan.
Oh, thanks. Yeah, let me just add that this is a very sort of casual kind of presentation, so feel free to, interrupt with questions, just sort of reiterating what Roseanne said. Okay, yeah, so I'm going to be presenting this work. It's pretty recent. It will be appearing in iClear this coming year. The title's a bit of a mouthful, but basically it's about outliers and their effect on the optimization trajectory of neural networks. Yeah, so if you've sort of been aware of existing studies of neural network optimization, there's like a large and growing list of observations of like what happens, and all of them sort of defy the traditional understanding of optimization in the sense that like we don't fully understand them. Existing tools can't really fully describe them. I'm going to just run through a very incomplete list. Don't worry if you're not familiar with every item on the list. It's just to give a sense of like the magnitude. So there's grokking, where first you memorize the train set, and then a long while after, suddenly validation goes up. The generalization benefits of large learning rate. Obviously, batch normalization is a huge benefit. The observation that you have these extreme outliers in the spectrum of the neural network Hessian during training. Progressive sharpening and the edge of stability, which I'll talk a little bit more about later. Simplicity bias, this observation that networks seem to fit like the simplest functions that they possibly can. The benefit of adaptive methods like ADAM, and the instability in a lot of training that you often don't see in like especially convex optimization. Double descent, training longer improves performance. Training with a larger model improves performance. All of these things are things that really set neural network optimization apart. And we haven't yet fully understood how they, arise. And we would expect that they'd sort of be related, but it's really unclear how. So I'm going to take a minute to go over this one specifically, just because it's particularly relevant. If you are not familiar with it, basically this observation, progressive sharpening, it was named by Jeremy, and also the edge of stability. So it's this idea, you're training a neural network, say, to do classification with the cross entropy loss, and you train it at all these different learning rates, eta, and here we have the loss as it goes down during gradient descent. And if we plot the sharpness, which is the largest eigenvalue of the Hessian, it's like the sharpest curvature in the loss landscape, it rises to precisely this value 2 over eta, and then hovers around that value for most of the rest of training. Okay, so, and like, what's the significance of 2 over eta? That it's the like stability threshold for gradient descent on a quadratic function. So like if you take a gradient step of size 2 over eta or smaller, the descent lemma says that the loss will go down monotonically at each step. But if you take a step at size greater than 2 over eta, then the loss will go up on a quadratic function. It's, it's an approximation. Meanwhile, the loss is going to decrease non-monotonically, because as long as the curvature is below 2 over eta, it decreases, in this ideal hypothetical like quadratic function. But every so often the loss spikes. So over time it's going down, but it still spikes up every so often. So this is the finding from this paper, and it's really just more evidence that like something more is needed. This kind of defies traditional understanding of smooth optimization, even of nonlinear functions. Okay, so in this talk, I'm going to present our finding, which is, yay, another interesting phenomenon that's sort of not understood. But I want to emphasize that like the goal is not just to sort of add to this growing list. I'm really hopeful that it can kind of unify these observations with a shared cause. I have this asterisk here because I want to just say that like I don't make this statement lightly. Like I am very skeptical of my own ideas. I've tried to like disprove this, and it continues to hold. So if you have ideas for like problems with the story that I'm going to tell, like please let me know. But so far this like really very naturally fits with a lot of existing observations. Okay, so just to show you like an experiment that'll just give you a sense of what the observation is. We're gonna run the following. We're gonna train a neural network like a ResNet with full batch gradient descent on CFAR10. And instead of tracking just the train loss, we're going to track the loss of each point individually. And then at some iteration, we're going to look at the change in loss of each training point from step t to t+1. And we're going to look at the samples that have increased the most from that one train step and those that have decreased. They have a very negative change to their loss on that step. So let's, let me just point out that we're doing this with full batch just to like isolate the effect. But in the paper, we also look at SGD. And if I have time, I can go into that as well. So like, what should we expect to see with this visualization? Like if you think about on any given step, the points that go up and lost the most and that go down and lost the most, what are they going to look like? So like, think in your head what you might imagine to see. So here are the samples that have the largest increase in loss. This is at some time step like t = 100. You can see a pretty clear pattern here. It's frogs and deer with a white background. And here are the points with the largest decrease in loss. And it's airplanes with a white background. And now if we do the same for ResNet, it's a very similar thing. It's trucks and automobiles that are red, and then non-trucks and automobiles that are red.
Can I ask a question?
Yeah, sure.
So you're talking about in some random time step, t to t+1. So I imagine the beginning that the set would be very different towards the middle and then the end.
Yeah. So
first, but then
sorry,
maybe airplanes learn first, but some other class learn second.
Yeah, so we'll see in a second like what it looks like over time. Okay. But yeah, you're absolutely right. Like the pattern, the precise like things that are largest and smallest change, right? Like whatever the pattern is. But this observation that at any given time step, you have this like semantically meaningful separation where there's like a clear pattern here. This occurs all throughout training. So maybe we'll get a better sense by looking at it over time. So we're going to visualize this over time. So here's the ResNet 18 trained with gradient descent. The first thing to notice is like we're doing gradient descent, but because of this edge of stability phenomenon, every so often you have the loss, go up a little bit, right? It's not decreasing monotonically, even though we're plotting the train loss, which is exactly what we're taking the gradient step on. Okay, so here's one of the groups. This is like just the first group that we found, and it's based on the background color, like blue versus white. The groups that I'm going to plot we're going to take the top 20 and the bottom 20 from each, okay? And keeping in mind that they were explicitly selected for the largest change in loss, so we're going to expect that somewhere they spike in opposite directions, right? That's exactly why we selected them. So here's what it looks like. There's the spike, and then there's a lot more spikes. And in fact, it continues basically continuously throughout training. You have this continuous process of these points oscillating in opposite directions with very large loss, right? So this is kind of, you wouldn't observe this in the full train loss, like it's very unclear that this is happening, but there's these very consistent large magnitude oscillations happening. And also the other thing to note is that these spikes sort of exactly coincide with these instabilities and the non-monotonic decrease in the or non-monotonic components of the train loss, that every time there's one of these large spikes, the full train loss jumps up a little bit. Okay, so maybe let's visualize another group just to see if this is consistent. So here's another one of the groups that we have. And if we visualize this, we see exactly the same thing, but maybe the big spike for this group is at a different location. But this again happens all throughout training. You might expect, okay, once we start getting close to interpolation, like the loss isn't jumping, it's getting very small. So shouldn't this effect be reduced? So let's now move, we're going to note the change in the x-axis. We're going to the end of training, and it's clear that this effect is significantly reduced. But keep in mind that the overall loss is still increasing. And so like, what's causing that? We selected these points at the time t that was like in the beginning of training. So if we now select these groups based on the end of training and visualize their loss, we get these massive spikes. So this is like, we're near the end of training, we've almost interpolated, and the training loss is like 0.5, 0.4, and you get these, small number of samples spiking to like 6 or 7. And this continues all throughout training with different groups, and you notice different patterns, right? So we went from background color to grass texture. So I think this is really interesting, and this paper arose from basically investigating what's going on here. So let's note some like common threads here in these groups. They're very prevalent features, often with distinct colors. And so by prevalent, I mean, it takes up a lot of the image. It's the background color, it's the grass texture, it's like a car, a truck that's red. They tend to begin very simple, something like background, and they become progressively more complex, like texture. And simple means something like available at random initialization, something that like a randomly initialized network would be able to pick up on. And these two groups, the like large increase and large decrease in loss, have gradients that point in opposite directions. So like if you're learning that red equals car, it'll massively decrease loss on red cars because you're making that prediction, but it will also increase loss on red non-cars. So there's these opposing signals. And so, yeah, we refer to these features and or the gradients as opposing signals. As everyone knows, the cooler the name, the more citations you get. So I asked ChatGPT if they had any better suggestions, and their best suggestion was backprop battle, which I thought was funny, but I stuck with my initial idea. So does this occur for every training sample? Like, does every training sample at some point become one of these points that's oscillating a lot? So here's the distribution of changes in the loss. You can see that like minus 2.5, 2.5 is like, it's very tightly concentrated around 0. So the samples that are oscillating are significant outliers. Not every sample at some point has this oscillation, but many of them do. And the other thing to note is that it's really centered at 0. Like on average, half the training points are going up or down on any given step. So like there's like every point is sort of affected by this oscillation in some way. What's causing this? Maybe it's a property specifically of the architecture, like we're using a convolutional network. But actually, no, the same thing happens with the vision transformer. You get different style of patterns, but you can still pretty clearly see these patterns here. Maybe it's a property of the modality, like maybe it's because images have like background color. But no, we actually found this with transformers on text. So here's two sort of opposing groups where the sequence that the transformer has seen ends with a colon, and then the token that it needs to predict is either a new line token or the word the, both of which are quite common in English. And if you train GPT-2 on open web text, you get exactly the same oscillation. Obviously, you can't do like actual gradient descent on this, so I just did SGD with a very, very large batch size, and you get the same pattern. Maybe it's specific to cross entropy. If you train a small MLP here on a polynomial, so on the left here is the training points that we're training a small MLP on, and we're using squared error, and the same thing happens. You get the same like outliers with very large magnitude changes in loss. Okay, so obviously, like we've looked into it a little bit, but like the actual process that's causing this to happen is still not very clear. So the remainder of this talk is going to give sort of our current best understanding with some experiments to back it up. We believe in general it's a consequence of depth and steepest descent. I'm going to give a really high level description. We really don't fully understand this mechanism. If there are parts of the story that you think aren't fully explained, you're correct. If there are parts that you think are wrong, you might be correct. Like we really don't know. So like we have experimental evidence where our story suggests certain results, and then we run experiments and verify it. And so like there's only so far that you can take that. But so far, everything I've tried to sort of invalidate this hypothesis of what's happening has failed. So. But if you have ideas, please let me know. So yeah, as I mentioned, it's like a reasonably descriptive story. And we also prove it for a simple model on a 2-layer linear net. So obviously that's simplifying a lot of things, but I do genuinely think that it captures some of the actual elements of what's going on. And like I said, it enables some pretty specific predictions, which we verify. And the story also sort of naturally fits with several other previous explanations that have been given for individual phenomena.
I have a question.
Yeah, this is a great time for questions.
Yeah, so there are also questions in chat, but my question is simple, like, you know the work on Grok, right? Some of the classic experiment they did is like a polynomial mathematical data set. In those cases, I find it hard to imagine opposite outliers in the data set. Can
Yeah,
you try that?
that's a really good point. So let me go back to the plot before. So we discussed this in the paper. If you look at the leftmost plot here, these points are the points that we're training on with mean squared error. And you're right that like there aren't outliers, right? This is like 20 points and it's a smooth polynomial. Like there are no outliers here, right? So when we use the term outlier, we're referring to outliers in the representation of the network, not in the input space. So what this means is there are points in the representation space that produce very large magnitude like activations in particular directions that are opposite and much stronger than the rest of the training data. And so we'll see in a little more detail like what precisely that means and how that affects training dynamics. But like here, this is what outlier refers to. So you can see that if you plot like the loss of just the orange and blue points, they're spiking to very large values. But then the loss on the other points is actually quite small.
So are you saying they come from the architecture or the optimizer of the model?
It's a combination. It's so, like I said, we believe that it's the combination of depth, which is one factor, and you'll see why, and the fact that SGD follows the gradient, like that you're taking you're following the direction of steepest descent, and the combination of those two factors, plus like the capability, that the presence of features that could, in some sense, like be differentiated. Maybe that's a little less clear, but
Okay.
yes, it's the
Thanks.
interaction of the two.
Thanks.
Maybe if there's some questions in chat before I
Yeah,
move on.
so a few people in chat are confused how you pick the groups.
Yeah, so remember we just like look at the loss change on every single gradient step, and then we just take like the top whatever 1% or top 20 that have the largest increase in loss and the largest decrease in loss on a single step, and then those are our groups. So sometimes that will include like multiple different signals, and then you can sort of distinguish it visually. So the images that I showed of like the white and the red, I chose those because they are particularly apparent. But like it's one of those things where you just like look at it and like you can clearly see that there are patterns. So we have like additional examples in the paper where you can like look, or I encourage you to try it yourself. Yeah, there's no like fully formal way of defining these groups other than just sorting them by loss change and looking at them.
And we're talking about training samples, right? Not validate.
Yes, these are points that are being trained on, but actually the same thing would happen on test points, and I'll show you that that's like related to the verification experiments that we run.
Okay, thanks.
I have one more question.
Sure.
Were there any differences in the batches of those training samples, or each batch showed a similar pattern?
Remember, this is full batch gradient descent.
Oh, it's full batch.
Yeah,
Okay.
so every gradient step sees every sample.
Thank you.
Do you see any correlation between the loss value of each point and this value of the difference which you use for differentiating two groups from each other?
Sorry.
Like, can you say that in some sense, like, I understand that these two different things, but is there a correlation between your type of groups which you differentiate and the fact that one group is a more difficult examples for the network, so you have a high loss on these examples, and the other group
I don't
is
think
the
it has
lowest?
anything to do with like difficulty of the examples explicitly. It's not necessarily the case that the network has high loss on like more difficult examples.
Okay. I just was interested, is there a correlation between these two?
Yeah, I mean, I
features of
guess
the
I'm not
examples?
aware of any definition of difficulty of a sample other than you could say like how long until it's learned and it isn't forgotten again. Like I've seen that kind of definition. But I think really this is just to do with like these very simple concepts like background color or whatever. I think we could maybe discuss it in further, but maybe
thanks.
once we've
Yeah.
seen like what's happening, and then it'll be like a little more informative.
Yeah, I think one thing maybe people get a little confused is the loss change. So it's a loss change before gradient update and after.
Right.
So the loss can be high or low.
Right.
So the
And in
sample
fact, the
can be a
loss is
hard
both
sample or
high
easy
and
sample,
low.
but
It
as
is
long as
both.
it makes a big
Yeah.
change
Yeah.
in either direction, it will be picked.
Yeah, I'm sorry for the confusing question. I understand that these are two different things. I just asked if there are correlation between them.
No,
That's
I
all.
understand. Yeah, I think we can discuss it further, but like I think maybe it'll be helpful to first go over like what we think is happening in more detail, and then we can discuss further. And I would also mention that we also looked at like for these groups, we looked at their gradient norm and their curvature and stuff like that, and they're outliers on all of these metrics, not just the change in loss from step to step. So they're very significant outliers, and they seem to be like really driving the optimization at every step. Okay, so yeah, I think probably maybe some additional questions might be answered if I like get into the specifics. So if that's all right, did anybody else have any like quick questions? Okay, great. So let me just reiterate. This is a very simplified story. I think Roseanne froze for me, so I don't know. Okay, can other people hear me? Somebody?
Yep.
Okay, great. So, all right. So I'll just keep going then. All right. This is really a story. We have experimental sort of verification of it, but and some mathematical analysis, but a lot of it is very high level. So just keep that in mind. Okay, so let's sort of visualize a hypothetical randomly initialized MLP, and we're going to assume that it has two input features. So this blue circle is going to be the sky feature. It's very large magnitude. It's very pervasive in the image, and again, that means that it's like propagated to many of the neurons because it's present in a lot of the image, especially if we have something like ConvNet. On the other hand, this sky feature is not really helpful for determining class, right? Like it's really only good for predicting the class marginal, P of class given sky, and it's not much help. It's not helpful for much anything else. The other feature we're going to have in purple is going to be the shape, right? This is very small magnitude. At random initialization, it may exist in some form, but it really needs to be learned and upweighted. On the other hand, it's much more useful for loss reduction, right? Like hypothetically, you can basically get perfect classification if the only thing you have is like the information about the shape of the object in the image. So really, this is like very abstracted representation of like a useful feature that needs to be upweighted and learned, and a sort of kind of useful feature that's very large magnitude at initialization and gives you an easy way to initially decrease the loss. So again, at initialization, any image with a sky feature is the output of the network is going to be dominated by the presence of sky. And let's suppose that at initialization, the network happens to, whenever there's a large sky magnitude input, it's going to predict plane. So on images of plane with sky, we're going to have very small loss at init. On non-planes that have sky, we're going to have very high loss because we're going to predict plane with high confidence on them. And on the remainder, we're going to have, whatever the average loss is. So at initialization, when we start optimizing it first, because we have a very high loss on these outliers that are non-planes with sky, it's going to have large gradients. It's going to dominate the gradient that we're following. And so when we follow steepest descent, we're really going to move towards rebalancing and predicting the conditional P of class given sky, right? That's like the first step. And actually, this linear first behavior has been previously observed in other works, this idea that like the first thing the network does during training is effectively fitting a linear model to the features that it has at random initialization. So what is that going to look like? We're going to have this rebalancing. So watch this loss and also the network, right? We're going to basically eliminate this overwhelming influence of the sky feature. And this is going to balance the loss between the outliers that are planes and that are non-planes, that both have sky in them. Okay, so once this happened, now like the network the gradient's no longer dominated by these sky outliers. And so now the network can upweight the more useful shape feature because that's like the path that's going to allow it to do, a better job at classification. And so since the outliers loss is no longer the dominating thing, we're going to visualize a non-outlier. So what this means is that we're going to remove this like input that is very heavy sky. And now we watch as the non-outlier loss goes down. And the way that this happens in practice, this is, again, previously been observed, is that the top singular vectors of adjacent layers of the network basically align, and it, amplifies some subspace and eliminates some other subspace. Like at a very high level, you're rotating into the like null space of the network, quote unquote, the uninformative noise, and amplifying the meaningful signal like the shape. So this is going to get upweighted. And so this has been observed in practice, right? You have this alignment of singular values. And as this is upweighting more signal, it means that the like shape feature is now being propagated through the network with greater amplitude, which allows us to, meaningfully use this signal to predict. And so you see that the loss on the most of the samples that don't have sky in them has decreased. So I like this is vaguely what happens at a high level, but I've left out one important part of this visualization, which is that as the network's layers align to amplify the shape signal, the sky signal is also being amplified because it appears everywhere, right? It's very prevalent. It dominates the input. So what we're visualizing here in the network is like the sort of hypothetical activation pattern for a non-outlier. But if we visualize what it looks like for one of the images that has a sky background, well, now it's going to add back in the sky feature. And this sky feature has now been massively amplified. And so now this is like a much larger magnitude feature that still dominates the output of the network. So this isn't per se a problem, because remember that this whole time we've sort of balanced, to predict P of class given sky, right? We've been predicting like the conditional, and that way we keep the loss between the planes and the non-planes balanced. So per se, this isn't a problem, but it does imply something important about the shape of the loss landscape. So because it's dominating the network's activations, the network now has a very large sensitivity to how the sky feature is used. So what this means is that if you were to make a small targeted change to say like, whenever sky appears, predict plane, it's going to massively decrease the loss on planes and massively increase the loss on non-planes. This is a hypothetical change that could happen, right? It's not what's going to happen initially during training, but the larger the magnitude of the sky feature, the larger the sensitivity to a change in how the feature is used. So if you make a small change to the weights, you slightly change how the feature propagates, but in a very targeted way. And this gets further magnified downstream and has a very large effect. And maybe now you have massive loss on the non-planes with sky. So in other words, I mean, like if you are not familiar with sort of the definition of curvature, this is basically saying that like the loss on the outliers becomes very sharp with respect to the parameters. A small change to the parameters can have a large effect on the loss. So this is effectively like the spectrum of the Hessian that is growing with respect to this feature. And this like observation about growth and sensitivity has been previously noted sort of like in passing with regard to certain like subcomponents of the network or the norm of the Jacobian of the network previously. Okay, so I realize that the story is very abstract, this idea that like you have this growth in the sensitivity of the network to a certain feature. Why should this matter? It sort of matches progressive sharpening, this idea that you have this steady growth in curvature up until you reach like the threshold 2 over eta. But let's like make it a little more concrete. We can tie it back to our experimental observation to see why this is sort of like a meaningful description of what's happening. So instead, we're going to sort of visualize this same process, but through a different lens, which is we're going to plot a 1D projection in parameter space. Like this is the loss function, as a function of the parameters of the network in 1D. And what this one dimension is going to represent is approximately, what do you predict when the sky feature is present? So all the way to the left is going to be, whenever you see the sky feature, you predict plane with effectively probability 1 very confidently. And on the right is going to be, you know, let's just say all the other classes, maybe equally likely, maybe not. But the point is you have these like two opposite ends of what do you do when the sky feature is present. So let's visualize what happens during optimization. So on the left here, we have the loss on planes. So we're going to like actually plot the loss here. And obviously, as you move more towards predicting the class plane when the sky feature is present, the loss on plane images with sky is going to go down naturally. And if you have the other images, it's going to be the opposite, right? Their loss will go down when you predict other. And as you move towards predicting plane, the loss is going to go up. So, you know, early in optimization, when we first start out, what's going to happen? Well, we're going to move down into the bottom of the valley, right? Because naturally, the average of these two is going to say, like, you should land right in the center. And then further optimization is going to sort of bounce around through this valley. Now, this is also something like all of these sort of individual components of the story have been sort of separately observed in previous work. So that this other work has a similar finding. And remember, we had this observation that, like, as you're bouncing around in this valley, so you have the balanced conditional P of class given sky, you're going to be upweighting the other signal that's more meaningful. And that is going to simultaneously cause the norm of the sky feature to get larger. So what happens, as we mentioned, the sensitivity to how the sky feature is used grows, and that corresponds to sharpening of the loss. So visually, you know, the loss is going to sharpen like this. And this is going to continue until we reach this threshold, 2 over eta, right? Or somewhere around there, right? It's not a perfect quadratic function, but at this threshold 2 over eta, the iterates that you take, instead of going, you know, staying in the bottom of the valley, are going to start to diverge out of the valley. And so each step you take is going to sort of geometrically increase in magnitude, moving away from the minimum here. So to make this image kind of complete, we're going to also visualize the loss on the non-outliers. These are images that don't have the sky feature. And obviously, because they don't have the sky feature, they're much less sensitive to how you use the sky feature. And so they're nowhere near as sharp along that. So what does the loss look like, you know, as you take these iterates back and forth that are sort of diverging out of the valley? So here's, you know, the blue loss, and here's the red loss, and here's sort of the average of the two, which is the green loss. Like I produced these literally by taking the average of two logistic functions and then taking a geometric sequence that was oscillating back and forth. But it's obviously surprisingly close to what we see in practice. And so the next question is, okay, like, you know, you're oscillating, but that doesn't happen continuously forever. Like how long does it keep going? So broadly, there seem to be sort of two things that can happen while you're oscillating. One is that the loss, you know, massively spikes. And in this case, you're taking like pretty large steps. And so you probably diverge. And in fact, there's existing work sort of observing this catapult or slingshot effect where you sort of diverge and then shoot off into a new basin that has often better generalization properties. The other thing that can happen is you go up a little and then it goes back down. So essentially the valley is like flattening, right? And so instead of diverging infinitely, you diverge a little bit and then you go back down into the center of the valley. And so, you know, a natural question is like, why should this happen in the first place? Like, why should it stop sharpening, right? We've seen why it should start sharpening, but like, why should it stop? And the answer is, when you're, you know, in the center, the losses are balanced, the gradients are balanced, and so you can sort of continue through the valley. As you start to diverge, the losses become imbalanced, but the gradients are maybe still not large enough to really massively affect the overall gradient, right? We're taking a gradient step on the full training set, and, you know, maybe here the gradient isn't quite large enough. At some point, the gradient on these outliers starts to basically dominate the whole gradient. And when this happens, there's two ways to decrease the loss, right? You're following the gradient at each step. So the gradient is going to point towards the network doing two things. One of them is you're going to use the feature differently, which is what we've been doing. It's why we've been oscillating, right? On the right side, we're saying that whenever the sky feature is present, predict like all the other classes. And that means we have very high loss on planes. And that means the gradient is pointing to, you know, whenever you see sky, predict plane more because you're not predicting it enough. So that's going to push us back across to the other side. But there's a second thing that's going to happen, which is that the fact that we have such a high loss on planes and the sky, the magnitude of the sky feature is the reason we have that high loss, right? We're very confident that it's not a plane. We're very confident in other when we see sky. And so another way to decrease our loss on these samples is to decrease our overconfidence by basically shrinking the magnitude of the prediction, which can be done by shrinking the magnitude of the sky feature activations. So the other way that you like the gradient points towards reducing the loss is by reducing the magnitude of these features, which will then sort of bring you more towards a less confident prediction, which is good when you're wrong, because a high confident wrong prediction gives high loss. So this other effect causes the magnitude of these activations to shrink. And so the valley flattens a little bit. And now we go back to the point where our step size is appropriate for the curvature, and we start to descend again. So I'm assuming that there were questions. Let me just, because I think Roseanne got disconnected. Oh, no, she's still connected. She just no longer in my, yeah. So were there any, did you see any questions, or maybe if anybody wants to chime in with questions at this point?
There's a very long comment. Maybe I'll ask them to ask themselves.
Oh yeah, I thank you. I like I iterated on this a lot to try to like make it understandable, because it is definitely a lot going on at once.
Do we see the same type of patterns for the first order as well as the second order methods?
Yeah. So the oscillation and that pattern does happen for second order methods. However, there are some distinct differences. And so we sort of initiate this. We have some experiments where we look at atom versus like SGD or SGD with momentum, and we see some interesting results that sort of suggest that part of the reason atom is so effective might have to do with how it handles this like process, or what would have happened if atom didn't do all its like little tricks. But you do still see some degree of oscillation. So I think that like understanding this effect for second order methods is like a very interesting wide open question that we like initially look into, but it felt like it would have been a whole nother paper, so we didn't want to like put too much in one paper. But yeah, I think that's like a really good sort of intuition for like what to look into.
Cool.
Do you have any intuition for how this story, I don't know, either stays the same or changes for like methods that prevent this kind of spectral growth of loss as you propagate through depth, like batch norm or renormalization kind of things?
Yeah. So I think in my mind, it's very clearly related. The exact sort of influence is not clear to me. So this pattern does happen even if you have batch norm, because in general, my expectation is anytime you observe progressive sharpening in the edge of stability, this is what's happening underneath, right? And so that finding is also pretty robust. Like that happens with second order methods. That happens when you have batch norm. That happens on transformers. And so my expectation is that like essentially anytime that's happening, this is happening underneath. But like as far as a more detailed explanation for like how exactly does batch norm, interact with this tendency is something that I'm very curious to look into, because I think that a lot of these methods that like improve optimization probably help because they somehow temper this effect or take advantage of this effect or something like that. So very clearly related, but like the answer is I don't really know. Somebody asked, is it possible to have one learning rate for some samples and another learning rate for others? So this is, yeah, so that's certainly possible. I think generally with regard to like progressive sharpening, whatever step size you have, the sharpness will continue rising until you reach instability. There are a few cases where that doesn't hold, but in general, that's the case. I imagine, if you took like these samples that have larger magnitude features and you reduce their learning rate, you might like change the order in which the patterns appear. But so like one of the things I tried experimentally was like when this oscillation starts happening, remove the outliers that are causing it and keep going. And that just causes the next set of outliers to sort of rise up to the surface and have it happen. So I think you basically, you have this occurring in multiple dimensions for all of these outliers like simultaneously. And it's just that the thing that you observe is really like the ones at the top. But like downweighting them is only going to cause the next ones to grow more. So I think it's not immediately straightforward how to sort of maybe mitigate this or use it. But I think that's like, thinking in the right direction for sure. Yeah, so the learning rate per feature, I think, is a similar idea, and like it might be interesting to play around with that and see what happens. On the other hand, we're actually going to see in a second that this oscillation is actually quite helpful. So part of this story is that I think the oscillation is part of why neural networks can generalize, despite like even gradient descent doesn't generalize as well as SGD, but like the interaction between like what oscillation does and how it affects the features, it's particularly this property that the oscillation is what allows the network to downweight this like simple feature and therefore might allow it to instead learn more complex features. And we'll see in a little bit more detail in a second. Would the use of large margin optimization at internal nodes help prevent this phenomenon? I'm not entirely sure I understand. By large margin optimization, you mean like something like the hinge loss? Could you maybe clarify what you mean by that? Because there have been some papers on large margin optimization at each node. Like you optimize on each node separately. My understanding is like logistic loss in the limit already approaches max margin. I'm not familiar with the papers you're referencing. And I guess it's not even clear to me, like, what would you be optimizing to have a margin for? Like, would you be trying to have the largest variance in activations across the samples or something? Like, that's not... Maybe we can discuss more, like, either offline or after. Yeah, any more questions? Yeah.
So if I understand correctly, we are just oscillating between these sharp and flattened valleys, and this pushes the network towards this region of edge of stability, right? Like with the increase.
So I think really most of the time you can think of it as a single valley. So there's a single valley that as you move towards the bottom of the valley and like move through the valley, it gets sharper and sharper because the magnitude of these outlier features is growing. And as long as you're at the bottom of the valley represents like the correct conditional distribution P of class given feature. So as long as you're near the bottom, it's fine for it to get sharper because you're still like using it correctly. But at some point, the sharpness, you reach the point where you're going to start diverging. And that's the edge of stability, right? Like now your step size is too large for the curvature. And so you start diverging out of the valley. Now, most of the time, it seems like you don't leave the valley. You just reach this point where the gradients of the outliers become so dominant in the overall gradient that the valley starts to flatten again because it's forced to downweight that feature in order to minimize loss.
Okay, sure. But if so my point is that these values are changing, right? Like here we have example of sky, but as you can, like you pointed out that it changes from grass texture to color of background.
Yeah.
And now I want to ask like more global questions. So looking, if we just plot the value of eigenvalue, so sharpness, we can notice that that overall it increases to overlearning rate, right? So my question is how it's related with this oscillation, like up and down with the flattened valleys.
I'm not sure I totally understood. So we're oscillating in this valley, and that is the up and down, yeah?
Sure, but at some point, the whole network is sort of hovering the sharpness to overlearning rate, right?
Yeah.
So like my understanding would be that at some point we are not oscillating as much. Do I understand it correctly? Because we have to stabilize.
So maybe we're not oscillating as much specifically in the sky feature. This is like a simplified visualization, the reality is that like the top eigenvector is going to be a superposition of many different features, right? And so the like most representative one at any given time is like the one feature that is changing in loss the most, but all the others are also oscillating. Like you remember how in that distribution, the plot that showed like at each iteration what's the distribution of loss changes, like the other features are also having oscillation back and forth. It's just that they're like not the dominant feature, and so over time it changes. Does that
Okay,
make sense?
thank you. Yeah, thank you.
I'm not sure if I fully answer your question, but maybe we can discuss further down the line.
Sure. I don't want
Just
to
to be
take
clear
time.
for everyone, like don't worry, like I don't know what the rules are for this, but I'm happy to stay on later and continue discussing if people want.
Yeah, it's great. We often go over time, but it's
Sure.
your timeline.
Yeah, okay. So let me move on then, and yeah, like I said, I'm happy to answer further questions, you know, even if it's past time. Okay, so sort of, you know, we have this high level story. It seems to match a lot of existing descriptions. And we have a little bit of like mathematical theory, like very basic. But really the value of any of these stories is in its ability to sort of predict what will happen if we do certain things, and that will inform future study and future development. And this is the component that has like convinced me. But you know, before this, I was like, oh, like this seems like a natural story, but it's so easy to sort of post hoc come up with a story that fits an existing narrative and be like, oh, I've solved it. But I've basically, you know, in all of my experience, I've consistently been able to say like, if I do this thing, here's what should happen, and every time it's borne out. So this is the part that like I'm very excited about, and if you have sort of suggestions for further ways of possibly falsifying or further refining the story, you know, please let me know, because I'm very eager to further refine this. So here's what we've described so far. We have this initial phase of like fitting a linear model where you essentially just descend into the valley and match the conditional P of class given whatever features you've currently learned. And again, this has been previously observed for several years now. Now we have the growth in activation magnitude as you sort of move through the valley. And this has also been observed, but it's like much less well understood. Well, the growth in sharpness has been observed, but this activation magnitude component is what we're part of what we're contributing to the story, and is what we think is currently like not the most clearly understood. Once you reach this stability threshold where the activation magnitude is so large that the curvature of the loss is too high and you can't descend anymore, now you're going to start oscillating and diverging out of the valley between, in this example that we've given, sky equals plane. So when there's sky, predict plane with high confidence, and sky equals other, right? And just the other meaning whenever there's a non-plane image with sky, you're going to predict like, I don't know, uniform over the others, or we're being intentionally not too precise here. And then lastly, this oscillation, you know, sometimes you're going to diverge, but one of the primary things we have is that you're going to have a shrinking of the magnitude of this feature activation. And the reason is because the two ways that the gradient says to reduce your loss is, one, you know, if you're predicting plane, you have to predict the other class more. And two, you're overconfident in the wrong answer. And so the solution is to reduce the magnitude of this feature. So like behaviorally, what, you know, we have this series of mechanistic processes that are happening. Can we sort of directly test that these things are happening outside of the existing experimental observations that we have? Sorry, that is my announcer that my cat, the automatic feeder, is going off. Okay, so we're going to test this out to avoid confounders. And this is what earlier I mentioned, like we do this on both the training data, but like it would also happen on the test data. And so the way that I'm going to show that is instead of taking a sample from the train or test distribution, I'm going to pass through this ResNet we're going to do the same thing. We're going to train it on CFAR10 with gradient descent, but I'm going to, at the same time, pass through it a pure sky image. I just took the sky color and I produced this image that is literally just all sky color. So there's no other signal in this image. There's no shape or texture for the network to be using. We're basically just seeing when the network sees sky, what does it believe is the, you know, how does that relate to the prediction of the network? And so if we plot this, we're going to look at the class logits for each of the different possible classes. And we see that early in training, there's this like smooth phase here. And this is like this smooth linear phase initially. And if we plot the norm of the last layer representation of this plain blue image, we see that it very rapidly shoots up. This is kind of zoomed out, but if you zoom in, it's like a very rapid rise. If you compare it to like the mean representation, it's not just rapid rise, but also much larger than most of the images in the training set. So this growth in the embedding norm, like we said, increases the sharpness. And once you reach this sharpness threshold, you start oscillating. And so you can see that the logits themselves, it's not just the weights, the actual logits that the network is predicting are oscillating very rapidly. And in fact, if we look at like this is the softmax, these are the probabilities assigned to each of the classes, we see that on alternating iterations, we either predict approximately uniform over the classes, or we predict very heavily plane. And in this case, you also predict a little bit of ship. But like it's despite the fact that like this was a very sort of overly simplified story, we actually directly observe this exact oscillation happening between class probabilities. And finally, like I mentioned, when this oscillation goes far enough, the gradient starts to encourage the network to downweight the magnitude of the sky activations. And so we see that slowly overtraining the feature norm decreases. So we did this with a bunch of other colors. We did it with an image that I picked, like the image that I tried to exemplify grass texture as much as possible. Like there's still a frog in it, but it's like a lot of grass texture. And this pattern consistently occurs, a sharp rise and then slow oscillatory decrease in magnitude. And you have, during oscillation, you have flipping in the class probabilities between like, one class that's heavily associated with the color and another class, or a couple classes that are heavily associated and all the others. So this, it doesn't happen as cleanly for all architects, but it's really quite consistent. Another aspect of verification here, as I mentioned, the oscillation is what allows these like quote unquote simple features to be downweighted. Simple, again, meaning that they're pervasive, they're very present in the image, they're readily available at random initialization, and you can somewhat use them like in the beginning to reduce loss, but they're not super helpful in the long run, right? So very simple features. In contrast to gradient descent, which hits the edge of stability, gradient flow doesn't oscillate. So we can sort of control for this and say like, okay, what is the effect of oscillation by following gradient flow instead? And maybe because gradient flow doesn't oscillate, it doesn't downweight these simple features. And so it kind of generalizes worse because it just learns to sort of memorize the samples based on their combination of simple features, right? And in fact, let me just note, I don't think I have the reference in this paper or in this talk. I do have it in the paper. There's a paper from like 2019 that is like towards understanding the generalization benefits of large learning rate. And they have a sort of very hypothetical theoretical model, which in the past I kind of thought was like, oh, that's nice, but does it really apply to reality? And in fact, it describes exactly this process. So I think it's quite related. Well, not exactly, but very similar. Anyways, sorry. So here's the experimental study with gradient flow. And you can see that the feature norm grows continuously with gradient flow. That's the gray line. And so basically without oscillation, there isn't this effect to force the network to downweight this feature. And so it just continues upweighting this feature as it moves through the valley. In contrast, the red is gradient descent. And initially, before reaching the edge of stability, it matches gradient flow with the growth of this feature norm. But at some point, you start oscillating. And at that point, you have this slow decrease, and it doesn't quite show on this time scale, but we saw that over longer timescales, it's a steady decrease in the magnitude of this activation. So in fact, it really does seem that this oscillation is very useful for reducing the magnitude of these features. And it's not something that I can state with certainty, but seems pretty clearly to me connected to the generalization properties of gradient descent versus gradient flow. And then connecting that to SGD, I think, is also like a really interesting future direction. So as I promised, we do run these experiments for SGD as well. It's much easier to identify the groups with gradient descent. So we took the groups from gradient descent and then we tracked their losses with SGD. And you can see that they have substantially larger variance than most samples. We actually, I'll show in a second, we tested that this isn't just because it's a smaller group. Like we took the average of a random subset of the same size, and it has much smaller variance. You can also see that obviously it's not going to alternate every step because it's not gradient descent, right? There's randomness. And also the groups are not always going to oppose each other, because in any given step, we might not take a step along the direction of like the feature on which they diverge from one another. But there are clear points where they very rapidly and with large magnitude, go back and forth in opposite directions. So clearly, this is like a very influential effect even during SGD. And in fact, it's my sort of impression through experiments that like basically almost the entirety of the gradient is fully explained by these few outliers in each batch for the most part. And so I think that also has like interesting connections to like batch norm, for example. So here's, as I promised, the plot of the same thing, but we took a random subset of training samples of the same size as the outlier groups, just to show that like it is a very high variance for the number of samples. So, okay, just to, wrap up and like call back to several good points that people have made that like, oh, this seems connected to X, Y, and Z. To me, it seems obvious that like these are potential connections. We haven't made them like very rigorous. This is again sort of like a very high level story at this point, and I'm like eager to understand more. But I think there's still a lot of work to be done. But it seems pretty clearly related to batch normalization and also adaptive methods. I'm quite interested in connections to sharpness-aware minimization. Very briefly, if you know how sharpness-aware minimization works, the positive gradient step is like simulating the oscillation ahead of time. And so you're going to downweight the features sooner, right? And so it's going to prevent the growth of these features and downweight them sooner. And so that might allow the network to generalize better by like gradient, SAM is to gradient descent as gradient descent is to gradient flow. It basically amplifies that effect and downweights these features. And of course, also the generalization benefits of a large initial learning rate. So maybe these and all the other techniques that we've developed work because of how they interact with opposing signals, how they help the network optimize despite opposing signals or some other way of handling them. And my hope is that this could help us design new improvements to SGD for training speed, for generalization, et cetera. Lots and lots of unanswered questions, including from you right now, which I'll be happy to get to. I'm really very happy to discuss this further because I'm eager to push this as far as it'll go, and hopefully it'll lead to a deeper understanding of what's going on. So yeah, here's the QR code if you'd like to scan. And thanks so much. I'd be happy to discuss further if anybody has any other questions.
Thank you. We can open up for questions.
Yeah, maybe one question.
Oh yeah, sure.
I think so. I think you mentioned that the gradient flow has worse generalization than something like SGD.
Or gradient
and,
descent.
Yeah, and this might be due to the lack of these kind of instability processes, right?
As a second order cause, like I think the main cause, to my understanding, is that it doesn't regularize the magnitude of these quote unquote simple features. And as a result, the network sort of just memorizes, combinations of these large magnitude features.
Yeah. So that kind of makes me wonder, like, is there anything you could maybe add to gradient flow that models this kind of process? And if you could get maybe the generalization benefits this way.
That's interesting. So keep an eye out. Jeremy Cohen is working on something. He's working with Alex Damian on something. I don't know when it's going to be put out, but it's on precisely that. They have sort of like a description of a flow. It's not gradient flow that tracks the trajectory of gradient descent, but without the oscillations. So I think that's probably worth looking at.
Okay, interesting. Thanks.
Somebody asked, by gradient flow, do you mean very low learning rate? Yes. So obviously I can't actually do gradient flow. So the solution is very small learning rate. And I basically just make sure that it's small enough that we never reach the edge of stability. So just very, very small. Yeah. Thanks for all the great questions. Hopefully this, please do go like play around with this yourself, because there's a lot that like I don't understand that I want to understand, and I'm hopeful. So
Yeah,
and
thank
thanks
you.
Roseanne so much. Thanks for having me.
No, it's such a lively session, clearly evidenced by all the questions. And thank you for spending extra time with us.
Sure, yeah.
Bye, everyone. Have a good weekend. Happy Friday.